Okay, example 2. For angle alpha in quadrant 1, sine of alpha is equal to 4/5. So let's start off by drawing quadrant 1. Okay, quadrant 1 is the top right quadrant, so if I just go ahead and focus only on that, I don't have to worry about the second, third, or fourth quadrant. Just make sure there's a lot of room for quadrant 1. And I draw a vector out into quadrant 1 such that the sine of alpha is equal to 4/5. Let's put the vector in a different color here, so maybe about like this. Doesn't have to be perfect. And if I draw a vertical line straight down to the x-axis like so to create a right angle, alpha is the angle right here in the corner. The sine of alpha's opposite over hypotenuse is 4/5, so 4 is the opposite, 5 is the hypotenuse. As always, the hypotenuse is always positive. I'm going up, so the opposite side there is positive. I'm going to the right, so the adjacent side is also positive. That's just our normal 3, 4, 5 right triangle. Majority of the problems in this section, they're going to give you perfect, like Pythagorean triples. So 7, 24, 25 is a popular one. 5, 12, 13, 8, 15, 17, 21, 20, 21, 29. There's certain things where they're all integer sides. They're going to give you a lot of those. But again, sine of alpha is 4/5, so opposite over hypotenuse are both known. Pythagorean triple, 3, 4, 5 right triangle. And just like that, I know the cosine of alpha is 3/5. The sine of alpha is 4/5. The tangent of alpha is equal to 4/3. Just like that, we can very easily determine the sine, cosine, and tangent of this angle alpha that we're dealing with. And what they want me to find is the sine of 2 alpha, the cosine of 2 alpha, and the tangent of 2 alpha. Alright, so just yesterday we did sine of alpha plus beta, cosine of alpha plus beta, tangent of alpha plus beta. So again, we had a property there, or we had an identity that allowed us to break it into sines of alphas and cosines of betas and stuff like that. Well now, sine of 2 alpha, cosine 2 alpha, tangent 2 alpha, once I got all these pieces figured out, I can just apply the property for each one. So sine of 2 alpha, according to the sheet, is 2 times sine of alpha times cosine of alpha. Alright, and the sine and cosine of alpha are both known, so the sine of alpha is 4/5. The cosine of alpha is 3/5. Multiply it all out. 2 times 4 times 3 on top is 24. 5 times 5 is 25. Just like that, I know sine of 2 alpha. Similarly, I can find cosine of 2 alpha. I got 3 choices for cosine of 2 alpha. I can use whichever one I want to use. I prefer cosine squared minus sine squared personally, but if you like one of the other ones better, by all means use it. You'll get the same answer regardless. I go cosine squared of alpha minus sine squared of alpha, and it is very important in this subtraction that we do the right order. Cosine squared does go in front. All this cosine squared means is square cosine, so 3/5 squared is 9 25ths. 4/5 squared is 16 25ths. The reason I like the cosine squared minus sine squared is because you get that common denominator already happening. If you do 1 minus 2 sine squared or 2 cosine squared minus 1, you got to get a common denominator. So cosine squared minus sine squared gets you that already. We go ahead and subtract, we get negative 7 25ths as the cosine of 2 alpha. Now, on the alpha plus beta problems yesterday, we did sine of alpha plus beta, cosine of alpha plus beta, and tangent of alpha minus beta. I did that on purpose so that we couldn't do what we're about to do here, and you had to work your way through it. I'm going to do this in 2 ways. Number 1 is the way you want to do it if it's possible. If you have to find these 2 anyway, tangent of 2 alpha, right, is what we're doing. I'll show you even a shorter cut than I'm about to take right now in a moment, but I want to show you where it's coming from so you understand why it works. Everybody agrees that tangent of 2 alpha, hopefully by number 1 on our identity sheet, is sine of 2 alpha over cosine of 2 alpha, right? And we just figured out, through a lot of really difficult work there, what sine and cosine of 2 alpha are, right? So I'm going to get, if I put sine on top, 24 25ths, and cosine on the bottom, negative 7 25ths. Multiply top and bottom by 25, I get 24 over negative 7, better known as negative 24 sevenths. Right? Even shorter than that, once you get the sine and cosine, they're both going to be over the same number in these problems. They just are going to be. Anytime you do these problems, they're always over the same number. You just take the top of the sine and the top of the cosine, that's what tangent's going to be every time. Alright? Now let's just say that we have a problem though that they don't ask us for sine or cosine, they just ask us for tangent. Okay? It's quicker just to actually apply the tangent identity. So if I use the tangent identity, tangent of 2 alpha, it says 2 times tangent of alpha over 1 minus tangent squared of alpha, right? So we get that. 2 times 4/3 is 8/3. I would actually probably do that in my head anyway. So that's what it looks like if I just apply the tangent of 2 alpha identity. 2 times that is 8/3, 1 minus that squared is 16/9, times 9, times 9, times 9. 9 divided by 3 is 3, times 8 is 24. 9 times 1 is 9. 9 divided by 9 cancels, minus 16. 24 over negative 7. Same answer. But again, if I don't have to find these two anyway, it's easy enough just to find tangent immediately. If I do have to find both of these anyway, I've already found them. Top over top, sine over cosine. Get you the right answer for tangent of 2 alpha.